Okay. So here is the syllabus, and I just wanted to indicate that I have updated certain things. The lectures are up to date, and also I have some section 4, chapter 3 notes. Those are not complete. I've started that process, but most of the notes are there. It's just that they're not formatted correctly, except for the first part. So we'll probably finish S3 today, and then section 4 in chapter 3 deals with S4 classes. I haven't decided at this point to what extent I'm going to delve into S4 classes. On the one hand, I would tell you that the vast majority of the people write S3 classes, even though the S3 classes are more informal. But the S3 classes follow a functional style of programming, which is the way most people who do statistics think. Whereas S4 classes are more formally defined, more like Java. And so I would say that probably 90% of the packages in R are written as S3 classes. But there's one important group of packages that are not written as S3 classes. And that's all the packages in the bioconductor project, which deal with microarrays and flow cytometry and proteomics and so forth. All of those are S4 classes. So, given that a component of this course is oriented that way, I would be remiss if I didn't give some attention to S4 classes. So I'm going to go over and load up the notes for chapter 3. And I'm going back. I want to look at two things. I want to look at the s3.r file, and I also want to look at the .omd file. And I need to clean up a few more things. Let me get rid of the console. And I'm going to set the working directory to linmod, which is the folder that contains the the linmod S3 environment that we're creating. So I have both of these up here. This is the R file, which has all the code, and then this is the sort of more explanatory file. Let me go ahead and knit that so we can refer to it. And in particular, let me just briefly go through what we did last time. Well, the first thing I did is I sourced this linmod s3.r file, which we'll go back and look at in a minute. And then, if I look at the linmod est, which is sort of the workhorse for computing these things, it's just a function of x and y, and the environment for this is in the global environment the way we're defining it. And in addition, here's the body. Now, there could be direct ways of computing this, but we're going to use the QR decomposition, which is what R uses to compute these types of things. And if you look at X, then we're going to compute, which is the model matrix, we're going to compute the QR decomposition of this. In a regression, that will be things just like the predictive variable and the intercept, potentially. So we compute the dr decomposition, which I called qx. And then you can get the coefficients for your regression model as qr, or solve.qr, of the qx plus the y. You need the y, which is a response variable, and that gives the coefficients. And then the number of rows minus the number of columns will be the degrees of freedom for the error term. The sigma squared will be the sum of the y minus y hats, and the way you compute the y hat is simply x matrix multiply times the coefficient vector, and that computes the y hat. And then I'm going to divide that by degrees of freedom. Well, I'm going to take that difference and I'm going to square it and then sum it up. So it's a sum of squares of the y minus y hats squared divided by the degrees of freedom. That's the estimate of sigma squared. The covariance matrix, which is the covariance matrix of, in this case, if I only have two parameters, beta naught for the intercept and beta 1 for a single x, then it would just be a 2 by 2 matrix, and it would be what you would have is the square root of the diagonals would be the standard errors, and then the off diagonals would be the covariance. I can show you where these are given shortly. And then I'm going to return a list structure. I'm going to return the coefficients, the variance covariance matrix, sigma, and the degrees of freedom. That's what I'm going to return. And this is this computing formula. So again, I could go back and I could actually look at the source code, which is given here. And notice there's some annotation here. So what I've been talking about is this function beginning on line 20. Now, I'm going to define linmod as a function and use method, and that indicates this is going to be a generic function. It's a function of two arguments, x and y, and I'm going to use method linmod, and that allows me to sort of use that prefix notation and then followed by with the linmod designation and followed by the class designation. I'll show you that in just a moment. Well, right below it, you see linmod.default is that notation. And in fact, you're treating default as if it's a class, but it's really the default if no other classes are found. So there's a certain convention we use in S3 classes, and you just have to get used to it. So linmod, which is the method name, dot class name. But I haven't been talking about this first function yet. I was talking about this particular function right here. This is the workhorse, and that's a particular function that simply computes the estimates, and it's a function that we internally use, and in particular it's used by the default method, the linmod.default. But again, I'm going to pass it an x and a y, and the x will be the predictors, and the y will be equal to the response. So I'm trying to predict y from x. But in this case, and if I have simple regression, there's only one x, of course. But I also have an intercept. And so there's sort of like two x's because one of the x's will be all ones because it's the intercept term that I'm using when I say y is equal to beta naught, the intercept, plus beta 1x, x is the predictor, plus some error term, epsilon. Okay. So again, this is what I talked about before. I've just sort of broken it out a little bit better. And so that function is the workhorse of what you have to compute. Now, going down, let me skip down here just a moment. This print method, print.linmod, print is a generic function. And so print, if I say print.linmod, print as internally within R, it is a generic function. It's been defined, excuse me, it's been defined the same way that we define a generic function up here. But print is defined internally to R. It's a generic function throughout R. And so I can use print as my as my prefix, dot, and then in this case, it's going to get applied to the class linmod. By the way, here's where I create the class. And so when this would be the short, what we call the short print, and it's just simply going to print the call, how we called it, and then it's going to print the coefficients, and that's it. Now, if you look at the LM function built in R, that's what it prints. Let me go back up and look at default for a minute. So if I go back and look at default, and so you're wondering, where does this function right here that I just talked about, where does it come into play? Well, it's defined within default. In other words, it's defined right here. So how do we get there? Well, first of all, linmod as a function looks at its first argument x and says, what is it? And if for example, it could be a formula. And there are a couple other choices we're going to have. But if it doesn't find it, then it goes back to the default, and it uses this routine. So in this particular case, I want to make sure I need to have x as a vector, as a matrix, and y as a vector. So I'm going to coerce x to be a matrix. As matrix, the as coerces x to be a matrix. So whatever x is, it tries to convert it. Now, it can't perform magic. That if you're too far off, it will make every attempt to convert it to a matrix. But a matrix has a structure in which all there's rows and columns like a data frame, but everything has to be of the same type. So in our case, all numeric. And then I'm going to coerce y to be a vector. So we say as dot numeric to convert it to be a vector. And then I apply, once I've done that, and technically, if you were writing this to be robust, you would actually put some error conditions in or some warnings or whatever. So if someone gives you the wrong form of x and you can't coerce it, it doesn't fit any of the other choices we have, then in that case, you should print out a warning or maybe even an error if it's too bad. It says, this is not of the correct type, it has to be of this, or whatever, but you should specify in a more robust implementation of this some sort of warning or error message. So I'm going to call the linmod est on x and y now. And that returns est. So what is est, E-S-T? It's what is returned by this function. But what is returned by this function? A list. So est is a list that contains these components. Now suppose I want to add some additional components to est. I can do that with the $ operator. So automatically I get these 4 components. The coefficients, the variance covariance matrix, the estimate of sigma, and the degrees of freedom. Automatically I get those 4. So when I do this, I now have a list, and I could extract, if I just returned est, and we do return est right here, at the very end we return est, I would be able to extract those 4 components from it. But I'm going to give it a couple more components. In particular, I'm going to give it the fitted values, s $fitted dot values, which is simply the y hats, and that's simply x matrix multiply. Remember that %* means matrix multiply. So I'm going to take x matrix multiply it by the coefficients. Again, I took s $ coefficients. They already exist. In other words, s $ coefficients, you can get that because of the previous statement. Because the previous statement defined est as a list, and that's one of the components. So I can now, at this next step, I can extract it. So I'm multiplying x matrix multiply times the coefficients, which gives me y hat. And then I'm going to coerce it to a vector. And these are the y hats. Now, again, R has a specific name for these, fitted dot values. And this has some advantage, as you'll see. Now, what about if I want to get the residuals? Well, the residuals are simply y minus y hat, y minus the predicted values. And therefore, it's y minus s $ fitted values. Now, notice that I can do that. I'm extracting fitted values from est, but that was defined in the previous statement. So again, I can do that. So I simply have y minus y hat. And in s $call, there's a function match.call, which actually just extracts how you call this particular, this particular function, the generic function linmod in this case. And so I define 3 new components of est. So not only do I have the first 4 defined up here, I have 3 more defined here. Then I'm going to do one more thing. I'm going to give est a class designation. This is key. Without this, it's not a class. I'm going to call it linmod. So linmod is both a class, but it's also a generic function. Okay, so this is these 2 functions are kind of the heart of the matter. And if you go back and look at this, I could say source. Okay, we can run that. And again, if we want to look at the arguments in the environment and the body, we can do all that. But let's take a look at this data set called cats. And I could look at well, let me just look at the head of cats. So I have sex, and then I have 3 variables here. I've got a categorical variable called sex, which of course is just male and female. Or F for female and M for male. I have the body weight and the heart rate. And I want to predict the heart rate from the body weight. But I also want to consider potentially sex in the model. So first of all, if we just do a linmod est, and here I'm C-binding 1, I'm trying to construct my X matrix. And how do I construct the X matrix? It's not enough just to have the body weight of the cat. It's not enough. I also need a 1 for the intercept term. So I'm going to C-bind, which means bind together. It's going to bind together a column of 1s with the body weights into a matrix which has 2 columns. Is that clear what we're doing here? So this binds together the columns of 1 with the body weight, and this says, so this is X now. And it's a matrix the way I've defined it. And then Y is equal to the heart weight. Again, I'm using the $ to extract it from cats. Now, if I would have attached cats, I wouldn't have needed those $. I could have just used the names. So if I attach it, then I don't have to extract the names from, in this case, the data frame. But I didn't, so we do. So if I run this, what happened here? Oh, at this point, I haven't actually run the model. Okay. When I run the model, what I get, I'm running linmod est. At this point, I'm just getting the coefficients, the variance-covariance matrix, I'm getting sigma, and I'm getting the degrees of freedom. Now, I think there were 144 observations. And so the way you get the degrees of freedom is 142 is the number of rows, which is 144, minus the number of columns in the X matrix, which is 2. And so it's 144 minus 2, or 142. And sigma is 1.45. Now, do you know if you take, in regression, if you take those coefficients and divide by the standard errors, you would get a t-test in the traditional way of doing things. So where do I get, so if I take the coefficients divided by the standard errors, I get a t-test. Where do I get the standard errors? Can anyone tell me? They're the square root of the diagonals of this matrix. These are variants. So in other words, this number right here is the variance of beta hat 1, beta naught, beta hat naught, the intercept. And the second one is the variance of beta hat 1. But I don't want the variance. I want the square root of the variance. I want the standard deviation. And that's what we call the standard error. So by taking the diagonal elements, and there's a function called diag in R that extracts it. So by taking the diagonal elements and taking the square root of those, you get the standard errors. And if I divide the corresponding standard errors into the coefficients, I get a t-test. And each of those would have 142 degrees of freedom. I didn't do that, but I could have. Now, suppose I run the regular R function Lm. So if I run the regular R function Lm, this is what you get from R. And we want to see how close we get to this when we do this. And VCOV is actually a generic function. And if I take VCOV of LM1 is what I call this, I will get the variance covariance matrix. So let's see what happens when we run this. Now notice this VCOV right here, computed here, is exactly the same as what we computed. In other words, this is good news so far. So far, we've checked a few things. We're replicating what R does in that built-in function LM. So that's good. Okay, are there any questions? Now, when I do C-bind, I can also define the column names. In other words, when I say C-bind, I say constant equals 1 and BWT equals cats $BWT. So if I look at X, if I look at my X matrix when I define here, and then if I say head of X, notice that I have now named the columns. So in the C-bind function, I can do that. And I'm going to define this. Now, if I run linmod of X and Y now, will it work? Well, let's kind of look at the choices we have. Let's go back to this other function here and see where everything is defined. Now, the way we've defined it now, we've defined this as a default is X is going to be a matrix and Y is going to be a vector. Or if it isn't a matrix and a vector, I can coerce it to that. But there's another choice we have, and that is that if X turns out to be a formula in the first argument, then we should also be able to do it with a formula. This is standard R practice, to be able to use a formula. So if it's not a formula, then it falls back to the default. Well, that's what's going to happen to us because I'm not giving a formula. So if we go back here and say, okay, what happens if I do linmod on x and y now? If I do linmod, notice the call, that's what I called it with, and then the coefficients, the constant is a minus 0.35, and the coefficient for the predictor is 4.03. And let's take a look at what R did when it used its built-in function, which is up here. Notice this is the call. This was called with a formula, though, which we're going to do. And then it gives this is different down here. I mean, this is giving the variance covariance matrix. But the basic print method gives this. And our basic print method gives this. So in other words, essentially identically the same. Okay. We're using the default method to compute things. So now I can do some things. So for example, if I want to use COEF, or the coefficient spelled out, is a generic function, so I can actually apply that. And so I can actually get the coefficients, which would be useful if I wanted to, say, plot and draw the line on the plot. I can actually also use fitted. And again, that's a generic function. And the reason I can do that, well, let me just do it. I can do that. I can do the fitted. And in this case, I'm only giving the first 5. And I can also get the residuals. And in this case, I'm only giving the first 5. Now, why can I do this? Why does this work? Because this is something that actually comes from the LM function and GLM and so forth. In other words, this is a built-in R generic function. So how could I use that based upon the objects I created? Why does it work? Well, the reason it works is because that fitted is really a shorthand for fitted.values. We can abbreviate in R with these as long as it's unique. And so if you look back here, when I define, I didn't mean to go here. When I look back here, when I define, where did I do it? I define these two lines of codes. And I call them fitted.values and residuals. And because I define them this way, this allows me to use the built-in generic functions. I got them for free. So I don't have to do any more work to get the fitted values, the predicted or fitted values, and the residuals. And this is good because a lot of diagnostics we do for a model, we use the fitted values and residuals. So we got that for free. But that would not have happened had I not used those names back when I defined those two additional components in est. In other words, when I define est in that way. Okay, well, so we're doing fairly well. We're reconstructing it, but in order to construct it better, we need to actually have a model way of doing formulas. And the way R does formulas is y tilde something. And on the left of the tilde is the response. And on the tilde, and then you have the predictor. You have some model equation. And that model equation, by default, it assumes the intercept is there. So I could say 1 plus x, but I don't need to because 1 is assumed. So I can just say y tilde x. And but that means, by default, you're going to fit the intercept and the x to predict y. In order not to have the intercept, you have to say minus 1. So if I say minus 1 plus x, it will fit x with no intercept. So in order to not get the intercept fit, you have to tell R not to do it. Minus 1 plus x fits x without the intercept. But be careful, because if you say minus 1 plus x, that forces the equation through 0. when x is equal to 0, y is equal to 0. That's kind of rare. If you're calibrating an instrument and you have an x and a y and you think that by the calibration that it actually goes through 0 and you're testing the calibration, then maybe it's okay. But there are very few cases where you want to force the intercept to be 0. Okay? So just be careful about putting -1s in that model. There are reasons to do it. If A is a factor, and you have a single factor, it's a one-way analysis of variance, y is continuous, then you're fitting a model mu plus alpha sub I plus epsilon sub ij, right? And you have to have constraints, because if you look at the model matrix, it turns out, let's say you have 4 levels of A. It turns out that the model matrix, the first column would be all 1s. And then for the ith group, you'd have a 1 in that position and 0 every place else. So for the first group, you'd have 1s, and then for the next 3 groups, you'd have 0s. That would be the second column. First column would be all 1s for the intercept. And the third column would be 1s for the first group, 0s for the first group, 1s for the second group, and 0s for the third and fourth. The problem is the last 4 columns add up to be the first column. You have a singularity. It doesn't work. So you have to put a constraint on. Now, R puts a constraint of alpha 1 equals 0. Jump puts the sum of the alpha sub i's equals 0. And SAS puts the last alpha equals 0. None of them agree. But it really doesn't matter, because if you think about it geometrically, I have this 4-dimensional space, and I'm projecting on it, and so I have y, which I project into this 4-dimensional space, and that projection is y hat. Y hat is written as a linear combination of the basis for that space. And the only thing you're doing by putting that constraint is you're finding a basis, but you can find that basis set in an infinite number of ways. And so whether or not you use the sum of the alpha sub I equals 0, alpha 1 equals 0, or the last alpha equals 0, it just forms a different basis vector, basis set for that space. And so it doesn't matter so much, except it does matter in some ways. That is the way you interpret the coefficients. Now that's true if you have A as a factor. But if you put -1A, it doesn't fit an intercept. And then you can just use dummy variables for each of the 4 groups. And you're estimating the alphas actually become mu sub i's. You're just estimating the means of those 4 groups. So if you put -1 plus A and A is a factor, it means I'm not fitting that vector of 1s. Therefore, I don't have that singularity. And therefore, my coefficients are now actually the means of the 4 groups, or whatever. In regression, though, you're almost never going to do it. You're almost always going to have an intercept that's not 0. Well, let's go back to the formula a minute. Suppose your first argument is, in fact, a formula. And then we specify the data in a list. Then the model frame is a function, and it takes the data and it takes the formula, and it only extracts. You may have tons and tons of columns in your matrix. Your data frame may have lots and lots of columns. But suppose you only want a single x and a single y. Well, what the data model.frame will simply extract the variables that you need for your model, and it just ignores the rest. And it puts the y first and then the x, or the x's if there's more than one x. And then from that, we construct a model matrix. A model matrix is a matrix representation of that. And it depends on the terms attribute of MF. MF is the model frame, or what I call our instance of the model frame. And then the model.matrix, and I'll go into a little more detail with an example later, but I can actually do it because we did LM1, right? So if I do model.frame of LM1, if I do that, then the model.frame in our case looks just like, well, it doesn't have the intercept term, but it has those two variables, the heart weight and the body weight. And notice that it put the heart weight, the y, first. So that is the model.frame. And I think I can do this directly on the matrix. Let me see if this works. What did I call it? LM1? Yeah. Now notice this is just the X part. Notice that it has one column for the intercept and one for B. It does not have the Y in it. So the model.matrix is the matrix we form for the right-hand side. But it's not just a matrix, because it also has an attribute. It also has an attribute. But it's basically a matrix. Okay? And then the model.response of LM1. Whoops, I may have to define. Yes, okay, I think I'm going to have to do that. I'm going to have to create a model frame object before I can extract the Y. So if I would, for example, if I would say model.frame of LM1. So I'm getting the model, I think this will work, yeah. So if I get the model frame of LM1 and then I do the model response, it just gives me the Y. That's all that is. So that's all I'm doing here. So again, I'm getting the model frame. Now this may seem trivial in this case, but a lot of times you have a data set. You may have a data set with 20 or 30 variables. So think of it as 20, 30 columns. But you're going to fit a model with maybe only 3 or 4 of those columns. Well, that's all that's going to be in the model.frame. That instance of that is just going to be the 5 or 6 you use, and it's going to put the Y first. So that it knows where the Y is. And then the model.matrix are the predictors, just the predictors, with the intercept, unless you've specified there is no intercept, with a -1. Now, once I compute X this way, X is now a matrix, and Y is now a vector, right? Which means I can call the default. That's the way the default is expecting it. So now I can say linmod.default. I now call it on X and Y, and I get EST. Now EST contains, it contains the, it not only contains the 4 things I originally defined in that worker function, but it also contains the fitted values and residuals. And it also contains the fall, actually, the call. But I'm going to redefine the call to be the formula. In other words, I want it to be the formula. And then I'm going to return est. So what I have done is simply reconstructed, with my formula, I simply take the formula and I deconstruct it so that I get the model matrix, which will be X, and the response Y. And then I call the default. Now that's sort of, if you look at your homework, if you look at the other one I did with the t-test, that's sort of the way you do things. Well, you don't have to do it that way, but that's the way these examples work. That we go back to the default, we decompose, whatever you do, you decompose it down and do a little data manipulation, and then you call the default. So that's what we're doing. So if we go back we go back. What I'm now going to do is I'm going to do something a little more complicated, in fact. I'm going to do cats.lin. I'm going to fit the function linmod, and I have a formula as the first argument, and the second argument is cats. Okay? And then let's take a look. This is the default print. Now I have a formula as the first argument, so I had to deconstruct it. But I'm not just doing the heart weight as a function of body weight. I also have body weight tilde asterisk sex. Now what does that asterisk mean? It actually means I'm going to fit three things: body weight, sex, and the interaction of body weight and sex. This is an analysis of covariance model. An analysis of covariance model is where I have a regression, but it depends on the level of my factor. So in other words, I'm not assuming, well, I actually want to know, is there a difference between the relationship between the body weight and the heart? Does that depend upon the sex of the cat? In other words, it might be that the heart weight goes up at a different rate with body weight for males and female cats. You follow what I'm saying? So if you think of it, there could be slopes of the two. If the two lines are parallel, meaning this, it may mean that the heart rate of a female cat is smaller than the heart of a male cat. And it probably also mean, if you look at the data, probably you'd also see that the body weights of the male cats are bigger, but they overlap. But there's some of the males are going to be heavier than the females, and some of the females are going to be lighter than the males. So they overlap. But the question is, are the slopes the same? So that interaction, body weight by sex, actually tests that interaction. And if you reject it, you would have to conclude the slopes are different, but if I accept that there is no interaction, that implies the slopes are the same. We're always hoping the slopes are the same because that's a simpler model, but they may not be. Okay, well, I haven't tested the hypotheses yet. That's going to come from the summary.
What is that number there? The 1.67?
Those are just the coefficients. There's only 1 degree of freedom. You say the body weight is a predictor X, and it only has 1 degree of freedom. Sex has 2 levels, but the degrees of freedom is the number of levels minus 1 because of that constraint. The sum of the alpha spies equals 0. So there's only 2 columns, but it gets collapsed to 1 column, if you think of it as 1s and minus 1s. And therefore, what happens is I only have a degree of freedom for the sex. And so that tests the sex effect. Well, if you had the standard errors, if I had the standard errors of those and divided them into that would test those effects. The last one tests whether or not the slopes are the same. And if they're not the same, then I can run. If they're not the same, then I can run a nested model that I can actually get my estimates of the 2 lines. You can actually get it from this too if you're clever. Okay. So at any rate, this is a more complex model. It's an analysis covariance model where I have a single predictor and a single categorical variable. But I want to check and make sure whether I have 2 regression lines now, one for male, one for female, and I want to know whether or not they have the same slope. I can't tell from this. Those are just some coefficients. I would have to know the standard errors, divide the standard errors into those, and then there's a t-test, each with 1 degree of freedom. Okay. Now, if I do a summary of this, I'm going to go back and show you the code for this, but if I do a summary, it may help to see the output before I show you the code, because you're going to see this is what we're trying to get to. So here are our estimates. This first column right here, these are the estimates. They correspond to these coefficients. Do you see? And now here are the standard errors. And here are the t-values, and here's the significance. So what do we conclude? So if I were, now of course, we're going to have to show how to compute that table, because that table is constructed by us. Okay, I'm not using the built-in LM function. This is us. So we have to program this table. Not as hard as you might think. So we're going to have to figure out how to get the standard errors. Well, the standard errors is the square roots of the diagonal of that V-cove matrix. It's not so hard. And the t-values are simply the estimates divided by the standard errors. And then the p-values, well, okay, we have a t-value, and we have if we assume there's a t-distribution, we have a quantile, we can compute the probability. And we're assuming two-sided. So again, I'll show you how to compute all these. So the p-value, what does this tell us? Well, it tells you that body weight is a very strong predictor of heart weight. That's not a big surprise. And that's very significant, 0.0008. That's a little bit less than 1 in 1,000, right? The p-value is less than 1 in 1,000. So we're almost certain that body weight is a good predictor. And it appears that both sex and the interaction are also significant, but not nearly so much so. They're significant at the 0.5 level, but just a little bit below 0.5. So sex is significant, and body weight by sex is also significant. And so everything's significant. What this means is we probably need an unequal slope model. That is, we have to assume that the regression lines, at least to some extent, depend on male and female, but not the same. Okay? So what is the code? How am I doing time-wise? So we need to code for this summary method. So here's summary.linmod. Again, summary is a generic function. And it's going to be summary.linmod. Deconstruct that. Well, summary is a generic function defined in R. And linmod is, we define it as both a generic function, but it's also the class. So dot class. This is a summary function applied to something of class linmod. And so we get an object. And if that object is of class linmod, this is going to work. If it's not, it won't work. So we're assuming we're passing it. And when we did this, you see, when I did this, it created, that linmod creates a, I'm saving it in something called cats.lin. I just made that name up. But its class is linmod. So if I look at its print method, and then if I look at the summary of cats.linmod, it's the correct class, because it is of linmod. Then it prints out this summary. Now, I'm first of all going to define, there are two things that we have to do. We have to define the actual method for the summary, and then the print method. In other words, this code up here, a summary of linmod, doesn't print it. It does the work, but I need a print function, a print method now. So let's look at the work behind the print, and then we'll see what the print is. So I've got to print this table, right? So if you look at this over here, the main thing I have to do is print the table. So what do I need in the table? I already have the coefficients. What I need are the standard errors. So I can compute the standard errors as a square. Remember I said there was a function diagonal? Okay, so if you take the object, and this will be a class linmod, $sign V-cove. That extracts the V-cove matrix from the object, which is of class linmod. And then DIAG will find it diagonalizes that matrix. It forms a vector from the diagonals. So it's a vector of length 2, which are the diagonal elements in the matrix. And then I take the square root. Well, the diagonal elements are the variances. I don't want the variances. I want the square roots of the variances. I want the standard errors. So now notice R, and this is one of the very powerful features of R. Notice that it's functional in the sense that I can take the square root of the diagonal of. I don't have to do these all as separate steps. That saves a lot of time. So that's quite a bit of work in one little short statement. And then the t-val is simply the coefficients of the object, which is already there, you see, divided by the standard error. And it does element-wise division by default. It takes the first one of, in other words, the numerator, the cove of the object is a vector, and the denominator is a vector. Divides the first element of the numerator by the first element of the denominator, first element, second element by the second element, third, and so forth. So it's doing element-wise division. Again, that means you don't have to put it in a do loop and go through all the possibilities. The length of, if you've got 10 coefficients, in most languages you'd have to go through a do loop 1 through 10. But here you don't in R. And then I want to form a table, TAB for table. I'm going to C-bind the estimate. The estimate is simply the cove of the object. And then the standard error, and notice I'm naming them, STD, I'm naming them something that's a little bit more readable, estimate. And then standard error, STD ERR equals standard error. The t-value, again, a little more readable, is the t-value. The p-value, now, notice that I'm taking the absolute value of the t-value, and, well, I could do 1 minus that and not have that minus sign, but I'm taking the absolute value and put the minus sign so it's in the lower tail. The other way is to take the absolute value and take 1 minus that p-value. But I get the t-value. It's a two-sided test. So wherever it is, if it's upper or lower, I'm taking the absolute value that's going to make it upper. Then I take minus, which puts it in the lower tail. And then I'm going to compute the area to the left of that, which is what PT does. It computes the percentile to the left of the particular t-value. And so, and then I multiply it by 2 because it's a two-sided test. And you have to also give it the degrees of freedom, that's part of the objects. It's one of the, from the objects, which was linmod. Remember, degrees of freedom is one of those initial 4 things we computed. And so that gives me the p-value. And then I'm going to form a list. I'm going to form a list which has the object $call and tab, TAB, okay, which is a matrix. Tab, TAB, it's C-bind, right? I C-bind it. It's a matrix. TAB, capital T, capital A, capital E, is a matrix. And I'm going to form a list which has the call with that matrix. And then I'm going to define RES to be a class of summary.linmod. Now, there's also a summary.lm. Summary.lm is built into R. It's a summary statement. It's a summary method for LM. This is our summary method. Summary is a generic function. This is our summary method for linmod. And so that's the class, and then I return RES. Okay. Now how do we print it? Well, fortunately, R has a little built-in helper function. It anticipates that these summary analysis of variance type tables are going to be pretty common with all these linear models and generalized linear models and so forth. And so it kind of helps us out. But before we do that, we're going to say call semicolon new line. And then we print the call. Then we print another new line. and then we're going to print the table. But how do we print the table? Well, fortunately, R has this little function called print coefficient matrix. That's the abbreviation for that. And so you pass it, you pass it to coefficients. There are certain options you have. The p-values equals true. You don't. In other words, we compute the p-values in that table, but we don't necessarily have to print it. And has p-value. Now x in this case is going to be this RES object. So it already knows about TAB. Okay. So by default we're going to print the p-values if there are p-values, and so that's the default. So the end result of calling summary on this object linmod will be this. Now you could override this and say p-value equals false, and it wouldn't print the p-values, but I don't know why you'd do that. Okay. So that pretty much looks like, well, if I see this one right here, let's go up and modify this, and let's do this. And then let's, so that's the default print statement. Okay, now notice that the only difference is that the rounding is slightly different. And the rounding is controlled by a global R option. So these and these are the same. Okay. I didn't save it, so let me, call this LM2. Well, I guess I already destroyed LM1, so maybe it doesn't matter. Yeah, it doesn't matter. I've already destroyed it. If I then say summary of L, this is built-in R. Looks almost identical. Now, we could have done this. We didn't, we didn't. I could have relabeled it, the title, but we didn't do that. But notice that we got a lot of things for free up here, like these asterisks and so forth. This is done by that function, that matrix function for the coefficients. And so if you look at the results that we have and the results that R has, built using LM, they're almost identical. With just a little tweak, we could make them look identical. Okay. Any questions? Now, I should mention to you that we went beyond just doing a little regression. We have an analysis covariance model. In other words, we have gone a long ways towards reproducing the LM function. Now, I say yes and no. There's a lot of built-in checking into the LM function. We're not being as careful maybe as we should. There's one more function, predict.lm. Suppose you, in fact, want to predict the y-hats, or maybe you want to predict new values. So you have a model, and you've got new data, and you want to use this model on the new data. Well, we need to allow for both. In other words, if I have new data, I want to predict the new data. And if I don't have new data, I'm going to predict the old data for every observation I have in the old data. So So I have the object, which is the model object, and then it says new data equals null by default. So, so if it's null, though, if there is no new data, in other words, I'm going to use the old data. So this says if the new data is null, then I want y to be the fitted of the object, which y is really the y hats. Okay, that's if I don't give it new data. Else, if it is not null, in other words, if there's a formula, and the model matrix, let's see, yeah. I now form a model matrix with the new data. In other words, going back to this model matrix with the new data, I form X. And let's see, where am I? Yeah. Okay, notice that I have an if statement nested within a nest. So I say, if this is true, then if you have no new data, then use y hat from the original data. Else, if, and so I'm going to have an if and an else. So if the formula object is not null, that's an exclamation point. If it is not null, that is, if it is a formula, then I'm going to form a model matrix based upon the formula and get X, and then I'll assign new data to X. Oh no, else X gets to new data, and then I actually compute Y and I convert it to potentially to a vector of X, which is either a model matrix or it's the new data, and I just take X times the regression coefficients, and that's my Y. Okay. So again, if I have new data, then it depends on whether I have a formula or not. If I have a formula, I use the model matrix to predict, or I extract the X from the model matrix. Otherwise, I use the new data. But again, I'm using the new data here in both cases. And I course it to a vector, and then I ultimately return Y, which will be one of the, which will either be this Y from the new data or the Y from the old data. So I have that prediction. Okay, let's see. I think I did that. Oh, so in this case, what's happening? Predict. What am I doing? Old data or new data? Old data. I didn't give it any new data. So these are just the predicted values. But a lot of times you want to predict new values. And then if you get a little more sophisticated, you want to put confidence bands on those predicted values. So we often want to get confidence bands on the predictions. And there were two types of confidence bands you could get. You could get a confidence interval or a prediction interval. A confidence interval would be on the mean response at those values of the predictors. And the prediction interval, which is wider, would be the prediction interval for a single observation. So if I were an admissions officer at a university and I was looking at a particular student and I wanted to get their predicted maybe GPA based upon their high school GPA, I wanted to get the college GPA as a prediction, and I wanted the prediction for that individual, I would use a prediction interval. But if I wanted to know of all students who were maybe male and had a certain GPA in high school, what is the mean prediction, I would have a confidence interval. That's something that's covered in STAT 312, maybe 311, 511, 512. Okay. We used to call those courses, the graduate courses, 311, 312, when we renumbered a number in this way. At any rate, that's the that's the gist of this. Now let me quickly show you the homework. I meant There's your second assignment. And let's nip this. There's not time to... I'm going to start on section 4 next time. I'm hoping to finish most of this chapter. I may go a bit light on the S4 stuff. So I'd like to pretty much finish this chapter before the exam. And I will talk about the exam a little bit next time. So, assignment. You turn in the .omd file as well as the HTML file. And I said you may want to develop code using a separate .r file, and then you could, sort of like what I did. I had an R file for the code, and then I had a .omd file, right? So I may modify that. I may want you to turn on all three, because otherwise the R code gets all embedded within the .omd file. So when I did this, I had a separate file for my S3, and then I used a lot of that, in this file. But you can perhaps build it in, but let me think about whether I want you to turn in 3 files or not. So you're going to do a one-way analysis of variance. Now this is sort of an extension of the t-test. And so you're going to do a use method one way, you're going to have a one-way default, and then you put in your code. I gave you the first line, which is defining a generic function called one-way. And then you're going to have options such as one-way.factor, where the z is actually a factor. But now remember, unlike the t-test, it can be more than 2 levels. And then y is the response as a vector. And then, but also as a formula. So y tilde x type of thing. And again, that's similar to what we did when we had a formula. And then we're going to have a print one way, a summary one way, and then you're going to have a print for that summary. So we did all that in our version just now, right? However, if you did a one-way analysis of variance, you'd also want to do a multiple comparison, presumably. So here you're going to do Fisher's LSD, least squares means. So in other words, you're going to implement Fisher's LSD for multiple comparisons. And you may need to go back and look at an earlier chapter in a 512 book on how to do that. And I'm going to plot the one way using side-by-side box plots. And then there's a data set from Fairway that you're actually going to illustrate all of this. Now, Steve told me that this library is in RStudio, but my code says otherwise. So I've got to check this out. That library will be there if it's not now. Steve told me it was there, but given that I just executed this. What now? Did I what? Oh, yeah, this is locally. Maybe if I ran it. Yeah, you're right. It's probably there. It's not on my machine. Okay. So that's the assignment. Now, I may add one more piece to this assignment. I just want to go ahead and give you, just to round it off. There are 9 parts here, and I may add one more dealing with some diagnostics, like residual plots, so that, because you're going to get fitted values and stuff, and therefore you might want to do fitted values and residuals, and therefore a diagnostic plot like residuals would be good. So I'm probably going to add one more part to this, but I wanted to go ahead and give it to you. Okay. That's it. That's the assignment. That won't be due until after the exam, though. But if you work on it, it may be a good study aid for the exam. Doing this assignment pulls together a lot of stuff. Knowing how to do little snippets of things, like the Chapter 2 assignment, doesn't mean you can write code at all. It means you can do little snippets of things. putting it together in a program is the only thing that really matters. That doesn't mean I'm not going to ask questions on things in chapter 2 and so forth, or chapter 3 in terms of the snippets. But again, ultimately, when you get out of here, you should be able to program in R fairly well. Okay. Any other questions? So I'll discuss the exam a little bit more, and I'll be talking about S4 classes on Wednesday.